Hello, everyone. Welcome to this webinar. The title today is Get Moving with the CMC FPGA GPU Cluster. My name is Yassir Hariri. I am Senior Engineer at CMC Microsystem. It's been over a decade that I am with CMC. My focus is around hardware acceleration, targeting heterogeneous computing platforms. And this is a part of a series of webinars we are developing to enhance researchers' capabilities in terms of acceleration. And this is related to a specific infrastructure we recently deployed. It's a FPGA GPU cluster that we are presenting today. This is available for remote access and for use. So our agenda today is as follows. After a quick introduction with CMC Microsystems, we are going to review a few basics concepts around AI, machine learning, and deep learning. Then we will present the CMC Cloud FPGA GPU cluster in terms of hardware architecture and software stack. Followed by that, we are going to present an end-to-end deep learning platform, which CMC is currently building to enable research and development in the AI space from training deep learning network or deep neural network on a large compute cluster composed mainly by FPGAs and GPUs, and inference on a low embedded FPGA devices that can be deployed at the edge. Followed by that, we provide a use case which is a convolutional neural network architecture and training implementation using Caffe, which is a deep learning framework. And we will end this webinar by presenting a live demo showing the acceleration on the different accelerators, including GPUs and FPGA, with the instruction on how to reserve and access the nodes of the cluster, followed by a Q&A session. So, few slides about CMC Microsystems. We are not for profit. The CMC is federally incorporated in 1984, and the main mission is to manage the Canada National Design Network. And our objective is to deliver micro and nano innovation capabilities. The services that are provided by CMC are essential for the research and training required to advance the digital economy. And this includes various priorities, including Internet of Things, 5G, quantum computing, AI, and other topics. So basically, the National Design Network is a Canadian-wide collaborative project between 66 universities and colleges to connect 10,000 academic participants with over 950 companies. The main goal is to design, make, and test micro-nano systems prototype. CMC Microsystems manage the National Design Network. We measure overcome by the number of publications and awards and patents, industrial projects, new startups, and the trained HQP that's moved to industry. CMC delivers key services to increase researchers and companies' innovation capabilities in Canada, and this includes design tools, fabrication services to create working prototype, equipment and services for prototype testing, platform technologies, training, and technology plan and roadmap. CMC engaged strategically in Canada and worldwide, and this is a slide summarizing the industrial supply chain, and this includes CAD providers, fab, nanofab, and access to universities' MNT labs. And basically, this slide summarizes the collaboration side of CMC. So CMC currently is constantly working with its partners, whether from industry or from academia, industrial supply chain. Currently, we are developing R&D project at CMC where we are looking for opportunities to collaborate with researchers and industry. And this includes some priorities such as deep learning and AI, as well as we have another project based on RISC-V. So if you have any idea about research idea and you want to collaborate with CMC, please contact us for that. Also services for emerging processes and products. So we would like to connect to early adopters, sponsorship, and we keep researchers at the leading edge for the CAD, Fab, and Lab. CMC provide three main services in CAD, Fab, and Lab. CAD includes state-of-the-art environments for successful design, and this includes a selection of high-performance CAD tools that are available via desktop or through CMC Cloud, as we are going to present some of them today, and include user guides, notes, and training materials and courses. Fab consists of services for making working prototype, and this include multi-project wafer services, fabrication and travel assistance, value added in terms of packaging and assembly, and in-house expertise for first-time rise prototypes. As for lab, we provide device validation to system demonstrations, so we offer access to platform-based microsystem design and prototyping environments, access to test equipment and on loans, and access to contract engineering services. So I just clicked on the hyperlink. I'm going to go back to the presentation. A few slides about CAD. The CAD tools, we offer over 500 CAD tools and modules, and over 500 individuals are using these. And this includes physical design kits, PDKs, training, and support. For Fab, it consists of services for making working prototypes. So multi-project wafer services that are available through 9 foundries worldwide, offering industrial scale manufacturing. And this is basically advanced technology access to microelectronics, photonics, optoelectronics, MEMS, microfluidics, and embedded systems, including TSMC, Global Foundries, AMF, IBM, and STMicro. CMC is the channel partner for Global Foundries in North America. Lab consists of device validation to system demonstration, and here a few slides to summarize the CMC Cloud Unified Architecture. It's an architecture allowing seamless transition between environments, the CAD, Fab, and Lab, and it consists of a virtual infrastructure, VM, and a compute infrastructure which is based on high-end processors with large memory to accelerate CAD tools. These are connected to a consistent storage. And the third component is the accelerator cluster that we are talking about today, which is mainly composed by FPGAs and GPUs. The CMC Cloud environments provide researchers with secure, high-performance, remotely accessible EDA resources for designs of advanced microsystem and nanotechnology. So it consists of pre-installed, pre-configured CAD tools, physical process design kits, PDKs, and persistent storage, which allow to use high-quality server infrastructure and accelerate design using these CAD tools. This environment run on a high-performance cluster, so CMC engineers provide assistance in utilizing this infrastructure, as well as domain knowledge about the CAD tools, and you have documentation reference design, for example, for NSYS, CAMSOL, Xilinx, and all the other tools. And it's a uniform array available in standard and large memory configuration. So here are the spec of this CAD compute cluster. Our main topic today is around the CMC Cloud FPGA GPU cluster. So this is a cluster that we recently deployed, and it is accessible today for remote access. And the main purpose of this cluster is to accelerate compute-intensive workloads in general. So different workload can be accelerated on this cluster, from machine learning, training, and inference, video processing, transcoding, financial computing, database analytics, networking, and quantum chemistry, molecular dynamics, climate and weather genomics. And this is a good platform to do prototyping, for example, for RISC-V. So there are 3 different nodes in this cluster. The first type of node is called Cerebro. Each node consists of 2 Alveo FPGA U200. The second type of node is Genesis, which is a 2 GPUs V100, and Synergy, which have both, 1 FPGA, 1 GPU. So we build this configuration to allow different type of deployment. For example, the first node, you can use the 2 FPGAs to do to accelerate inference on this cluster. As for the 2 GPUs, is to perform your training of deep learning network on 1 GPU and scale up to 2 or even more. And the third one, if you need to run a project where you need a variety of accelerators in 1 node, in this case, you have access to both in 1 node. So as we will see in the step-by-step guide on how to reserve this node, you have the choice to select the node that is of interest to you and use it. So we'll have a demo about these nodes later. The research in the public cloud, this is a new service offered by CMC, and it is the Cadence University software program, which allow access to leading edge technology through the Cadence Cloud Passport program. So this is available everywhere in Canada and also in US, and people can access it today. Now, a few slides about AI, machine learning, and deep learning before we jump into the demo. The AI is an area of specialization. As you notice today, AI is is integrated in almost every device, and it's transforming almost every business. Every business is trying now to integrate AI in services and products to enhance users' experience and to make life easier for many people. So there's an explosion of ecosystem of tools, making it more accessible to even non-experts. And the area of specialization that are increasingly, in terms of investments, gaming, natural language processing, which will transform our life for example, in education, where kids can interact with the machine and they can learn a lot of things. Computer vision, most of the application for computer visions are in robotics and autonomous car, and it's very, very important field in deep learning. There are a few concepts. So AI is a system that consists of some new features that are make the system learn from its environment. So it needs some sensors, sense, reason, act, and adapt. Machine learning consists of algorithms that are improved as they are exposed to data over time. And deep learning is a subset of machine learning. And it's a very growing field. It consists of multi-layered neural network, such as convolutional neural network, which is a deep learning model that learns from vast amount of data. So in deep learning, you have 2 phases. The first one, for people that are new to this space, you need to use a set of training sample data to determine the optimal weights of the artificial neurons. So this is deep learning training. You have a network that you train on specific data sets to solve a specific problem. And once your deep neural net is trained, then you deploy for inference. which consists of analyzing specific data using previously trained deep neural nets. So in general, after a neural network is trained, it is deployed to run inference. For example, classify, recognize, and process new inputs. So the most important drivers or the rising popularity in deep learning is due to three key enablers. The first thing is greater availability of large data sets containing more training examples, the availability of efficient use of accelerators such as GPUs, FPGAs, and custom hardware such as the tensor processor from Google. And every major vendor is looking for a new innovative architecture to accelerate deep neural network. So there is a fierce competition there, and also new innovations around the algorithms. So we have new networks doing different things, combining of different networks, and of course open source machine learning flows, such as the machine learning libraries. So here a few slides to summarize in general the hardware as well as the software specification of the FPGA GPU cluster. So as I mentioned earlier, you have three types of nodes, and each node has the software stack for machine learning installed. So we have Docker containers. Today we have tested Caffe, TensorFlow, and PyTorch on all the nodes of the cluster. So there is a tutorial that shows exactly how to use Caffe. We didn't release a tutorial for TensorFlow or PyTorch, but they are already there. So if you are familiar with these, you can use them. So the software stack consists of the applications which can be in machine learning or in database or video or finance or genomic. And the machine learning framework that are available through Docker container. We have a variety of libraries that can benefit from the acceleration provided by the hardware, including CUDA neural network. We use support languages such as C, C++, Python, OpenCL. And there's a unified runtime and OS that can deploy these tasks to the hardware, which is in this case either the GPU or the FPGA. The end-to-end deep learning platform. So this is a very high-level slide showing the steps that you need to follow to do research in deep learning. As I said previously, there are two major steps, which is training and inference. But you can always start by prototyping using your desktop. Test, for example, the formatting of your database that will be used for training, the selection of the neural net, and then when you are ready, you can use the cluster in order to accelerate the training. And we will show how to do this. And once your model is trained, then you can deploy for inference. And there are two distinct spaces for the inference, either in the cloud or a data center. There are some very good candidates for that. Or you can choose to deploy on an edge devices, and this is for ultra low power inference in a mobile space, such as in autonomous cars or in a phone or on an edge device. And the flows are really different in terms of requirements and in terms of design. We will show some of the flows we are working on currently. So since the cluster is a multiple node, there are two types of deployments. Either you have different networks that you train on different data sets on the different nodes, or you have a large network that you can easily partition across the nodes and train it using different data sets or different, I mean, you have a large data set, then you can easily merge these data sets or partition them across your network on the whole cluster. So depending on your interest. to see a use case, a practical use case for deep learning training and inference, so we have a reference design that shows a novel platform of AI. It's an object detection, classification, and tracking using heterogeneous computing architecture. The first step is to select the data set that you will work with. Then you need to design the network. Either you design your own network or you use a predefined network, such as GoogleNet or AlexNet, and you train on the high-end cluster. And once the training is done, the trained network is then prepared to the next phase, which is the inference. So there is a lot of steps before doing that. The inference, you need to quantize your network, you need to optimize it to fit within a small device. In this case, we use the Xilinx ZCU102 for inference. And we basically take video frames for input, and we identify different objects that are part of the classes that we train the model for. So this is the cycle for training and inference for this project. And this is available on the FPGA GPU cluster. This slide provides a high-level unified design flow for advanced computing. And this is something we are working on currently at CMC. So there are different flows here. The main idea is to take an application from different spaces, for example, 5G or image video processing or AI, computer vision, then offer a path to this hardware platform. Either we are interested in low power specialized engines that can run on an edge device, edge FPGA device, or a accelerator architecture that will be deployed in the cloud. And this is for the right side, this is the FPGA-based design methodologies. On the left side, we have a target, either a hardware emulator or an ASIC. So basically, the flow consists of supporting high-level algorithms that are written in high-level languages such as C, C++, System C. Parts of the flow we are working on currently is a flow that uses HLS in order to generate an optimized RTL and do hardware-software co-simulation to target one of these target platform that CMC is supporting. As for the processor-based design, we currently support RISC-V. We have a few projects on RISC-V. And if you have ideas about RISC-V specialized cores and you would like to propose them to CMC, please contact us for that. So for RISC-V and ASIC, we support ASIC Designer currently. And the main goal is to offer a flow that can help researchers to take a high-level idea and use open source RISC-V, for example, in order to do some customization depending on the objective, and generate the optimized RTL, which can be both for RISC-V based or and algorithmic. So you have some functions that are mapped to the hardware. You have the RISC-V cores. You generate the optimized RTL. Then you can either target an FPGA flow or ASIC flow. The Alveo workloads acceleration. This is just a table showing the acceleration of some application using the Alveo board. So Xilinx released this, and for the machine learning, you can reach 20x speed up for deep learning inference. And here you have some other numbers. For example, for database, it's really very, very interesting, 90x. And financial computing. So there are some libraries that we can make available if you are interested in these spaces, but our focus today is machine learning. As for the GPU, the GPUs offer, as you know, traditionally speaking, GPUs the best candidate to accelerate deep learning training. And the figure of merit is 40x faster than regular CPU. A GPU can offer 40x. So this is very, very interesting speed up, which enabled the first wave of deep learning innovation. So before jumping to the demo, I'm going to talk a little bit about Caffe framework and basic concepts. So Caffe has a variety of features that you need to understand before start using it. The first one is the type of data that you can use in order to feed your network on Caffe. So Caffe currently support level DB, LMDB databases, HDF5, and raw images. So basically we use most of the time the LMDB because it offers very good efficiency in terms of feeding data to the network. And the processing tools that are available within Caffe allow you to create the database LMDB based on the raw images that you have in hand, and the generation of the mid image, training and validation set creation. So you need to create two sets, one for training, one for validation. And this is already automated by the tool. So you can just use the scripts to do these steps. You need also to use some data transformations such as image cropping, resizing, scaling, and mean subtraction. So basically, this is to change the resolution of your data set to fit with the model that you select. Caffe uses protobuf model. It is introduced by Google, and it is a good method for serializing structured data. It is human readable, and it is used to define a network architecture and training parameters. So no coding is required. So the model is the model that you use in a deep learning application can be described using this type of protobuf model. So basically, it consists of blocks. These blocks perform computation on data, and it also offers connectivity between these blocks. So the blocks, they are in three main categories. The first one is loss function for classification, softmax, linear regression, and other blocks. The available layer for computation, as you know, convolutional neural network are a series of convolution, polling, normalization. So you have access to this block. And the activation functions, it supports the ReLU, sigmoid, and other activation functions. If you take a deep learning model such as GoogleNet and AlexNet, they all share the same properties, which is a series of convolution, polling, and activation. And here's an example where we feed an image to our network. And this image is used to do a series of computations. So basically convolution layers, polling layers, activation layers. The last layer is the fully connected, which is basically a matrix multiply. And it calculates basically the probabilities for each class that you have in your training data set. And the result is the highest probability class of the object that was in the input. So now we will show a use case for CNN architecture and training. This is a good starting point for people doing using CNN for training and inference. And it showed the basic steps that you need to follow in order to implement this. So the first thing is to understand your data set. So you need to have access to a specific data set. And this data set consists of classes. So here in this case, we use, in this example, the DLRSD data set. It consists of 21,000 images. The resolution is 256 pixels, and there are 20 class labels. So each class is, for example, the river is a class, the runway is a class. So you have different classes that you add. And this is your data set, basically. So the two scripts that we provide, the first one is copy all the images from the directory to one destination directory. And then we create train.txt and val.txt, which are text files that provide the name of the files and the class ID of each file. And the second script, it resize all the images to fit with the model we are using, which is 227. And it creates the data sets for training and for validation in the LMDB format. So you have access to this script and you can modify them to fit well with your objective. So to show this, the first script here, it takes all the images in directory, put them in one directory, and create the val.txt and the train.txt, which provide the name and the class of each image, and the create dataset LMDB. As a second step is to create the database that will be the starting point for your training. The second step is the model definition. So we know now how to prepare data for training. The next step is to define the model that you would like to work with. So you need to select a convolutional neural network architecture and define its parameters in a configuration file. It's called, for example, CaffeNet proto.txt. In this demo, for example, we show the CaffeNet model, which is a replication of AlexNet. So it's a model, and the first modification that you apply to these models that are so you have different models from different contributors. For example, you have GoogleNet, AlexNet, VGG, and these models, they are originally trained on ImageNet, which is 1000 class. So you can take any model and adapt it to your problem. So for example, if you have 20 classes, you need to change the last layer, which is the fully connected, from 1000 to 21. So you need to open the file in the text editor, and you need to do this modification. The first one is the mean binary prototype. So this is an image that you generate during the dataset preparation. And you need to provide the path to the training dataset and the validation dataset, which you already generated in the previous step. And the second change is to change the number of classes from 1000 to 21. So to tell Caffe that you are working with 21 classes and not 1000. And this is so it works. You can visualize graphically each graph. So we have the script to do that. And you can see the series of convolution, pooling, and normalization. That will show you the structure of your graph. So for debug purposes and understanding purposes. Now, the third step is the solver definition. So we said the first step is data preparation. The second step is the model preparation. Now you need to define your solver. And this is the last step before training. The solver, it provides the parameters to Caffe to perform the model optimization and guide the training process. This is a very important file. And the first thing, it tells Caffe where your model exists. So at the path to your model, then you define the hyperparameters that you use. And this is based really on the size of the problem, on your understanding of the data. So there are some default parameters that you can start with, but you need to adjust them if you don't have good results. You can take a snapshot of the training for each number of iteration. For example, in this case, we take a snapshot. Each 2000 iteration will generate a file that provide the weight of your network at this particular iteration. And you can define the solver. So here you can either use the CPU or GPU. So basically, if you install Caffe on your desktop, you can use your CPU to see if it compiles and if your training is performed well. But for training large models, it takes a lot of time. So once you are sure that your model compile well and your data is ingested by the model, you can then switch to the high performance computing cluster to speed up the process. Now the last step, and now you are ready to do training. So basically you just issue this command, Caffe train, you offer a path to the solver, and then the path to your training log where you store the training results. And you will see something like this in the terminal showing the progress of the training. And you have also the path to your training results. In this case, we did a training from the dataset using a fresh network, and we achieved the accuracy of 85% after 4,000 iterations. It didn't improve. So to improve this model, we applied transfer learning. Deep learning experts are very familiar with this, and they use it all the time to fine-tune a model. So the idea is to, since CNN require large data sets and a lot of time to train, you need to use fine-tuning in order to achieve great results very fast. And it consists of using an already trained model. So you have already trained weight that you use as a starting point, and then you train for your problem. So basically, you need to tell Caffe to use the trained model, for example, for ImageNet, and then train it with your new data. So basically, you define the model and solver, and this command show how to do this. So basically, you set the solver as the previous step. But the new thing here is you specify the weight that you will use, and you can download this pre-trained model from Model Zoo, which is a library for pre-trained model. And the results here are more interesting than before. So instead of 80, we achieved 98% very quickly in this example. So this is a good way to do training on a new data set, is to use previously trained models. Now we are ready to switch to the demo. So I will show quickly a demo for this cluster on the GPU, and then we will switch to the FPGA. So I'm going to show you first of all how to access the cluster. So there is a web page for. I will just go to the web page for the cluster to show some resources. So if you go to cmc.ca, okay, the internet is very slow. Okay. So there is a web page for this cluster. I will just go to, let's see. So if you go to the web page of CMC, you go to the lab tab, and then systems, and then you have access to all what you offer at the lab. So basically the FPGA GPU cluster is available here. So you have some good resources here, including if you are a new user, you can follow these steps, request access, and fill the form. If you are an existing user, there are a lot of information that we have posted recently, including the quick start guide. And this all provide you with all the instructions on how to reserve and access a particular node. There is a tutorial and user guide that shows step by step how to do training on GPU and inference on FPGA. Data sheet, and also webinar recordings and webinar slides. So if we see take a look at the quick start guide. So the quick start guide basically provide how to access the cluster. So you need to to click on this link. We are going to go through this very quickly, but I'm going to show you exactly the main steps. So you need to submit and create an instance. Let's go through this live to show you all the instructions. So when you click on that link, you will be redirected to the VCAD webpage. And here you have the 3 types of compute nodes: Cerebro, Genesis, and Synergy. Since I already created an instance, so if you create instance, for example, for Synergy, it will provide you with a window here. Okay. Let's see. So since I already created an instance, it will be available on my Manage My Instance. And then here you can either connect, delete existing instance, or extend it for a number of hours or number of days. So if you want to connect to an instance, you click Connect. And then you have a new window showing you how to connect to it. So it's provide you with the user ID, which is your CMC email or the email that you use to register to CMC, and the password that you use to register to CMC. So basically I do Open Connect, Open Terminal. Then if I click on this window, this file that just downloaded, it will provide me with the access. So now we will show you how to do training on the FPGA. Everything you need is on the directory scripts. So you have 2 directories under scripts, NVIDIA and Xilinx. Let's have a demo on the NVIDIA GPU first, then we switch to the FPGA. So on NVIDIA GPUs, we have tested these 3 frameworks: Caffe, PyTorch, and TensorFlow. So depending on your interest, which framework you want to use, you can launch the containers using this command. So let's launch Caffe. And now the environment will change. So we have loaded Caffe, but before that I will exit the container just to show, because I have some question about how to exchange data between the container and the environment. So I will show how to do that. If we take a look at this file, it's a command. So basically you need to specify which directory from your home you need to map the data. And on the other side is the directory on the container. So anything you copy from the container to the data will be available on your home directory. So let's launch the container. And we are going to follow a step-by-step guide in order to do training on the GPU. So we'll have a simple example, because the example I showed in the webinar is pretty big. So this is a small example. So we are going to train a simple model. The first thing, we are going to get some data. And second thing, we are going to create the data set for the training. So these are the steps. Of course, you can look at this script to see how the reference design work. And then we are going to train the data set, train the model using this data set. So this is the output of the training process. Basically display the iteration and the loss results and the accuracy results. And once it's trained, it generates all the required files that you need. So basically, if you look at this it loads the network. It targets the GPU Tesla V100. So we issued the command here. So basically, it will load all the libraries that are required. It shows you which GPU you are targeting. For example, here we target Tesla V100 PCIe. And then this is your solver. So the solver, this is where you provide the path to your model, and then the training processor Caffe load the model and perform the training and generate some results. So this is the demo for the GPU. Once you are done, if you want to copy some results from your container to your home directory, you just need to copy them here to this directory, which is I showed in the beginning. So everything you copy here from the container will be available to you when you exit the container. So let's now exit the container. This summarizes the demo for the GPU. Now we are going to see the demo for the FPGA. So we'll just have one slide to explain a little bit how Xilinx provide the flow for inference on their FPGA Alveo board. So there is a white paper that you can see here for more details. But basically, the first step is your framework. So either TensorFlow, MoxNet, or Caffe. The front end consists of using their framework tensor graph to Xilinx tensor graph. So basically, they convert the graph or the model, the proto-TXT, that is used in training on the GPU, and they optimize it to fit with the FPGA devices. There are two main elements here. The quantizer. So basically, quantization is a very important process between training and inference. It consists of reducing the resolution of your data to fit with FPGA devices, and it uses as input the model weight in the calibration set, and the compiler, of course, to generate the software stack that will be used in order to do the inference on the FPGA. This is taken to by the runtime, and it generates the FPGA layers and the CPU layers. FPGA, they use overlays. This is a pre-configured hardware that is already mapped to the FPGA for deploying deep learning models. So let's see a demo on the inference on the FPGA, and maybe take some questions during the demo, because the demo, it has some steps that will take some time. So the first thing we are going to do is to load the container for the FPGA. So here I was disconnected. I will just reconnect to my session. So we'll go to my scripts. For the FPGA, we have tested Caffe, but we are currently testing TensorFlow for the FPGA. It will be released very soon. So I'm just going to connect this window. Okay. So the first thing, we need to load the container using this command. So my container is here. Once the container is loaded, we can start a session with docker run sh. Now the container takes maybe a few seconds to load, maybe 30 seconds. We will wait a little bit. But basically, this demo show Inception V2 SSD model in inference mode on the GPU. Now the image is loaded. Now we are going to run the Docker container to load the FPGA platform. So now we are on the machine learning suite from Xilinx. We will need to download the few datasets. I already downloaded them. We just need to copy them using this command. So we'll copy them. So once we copy the VOC test, we will unzip this data set. We generate this file in order to. This is a ground truth file. It's like an equalization file, and now we are going to get the necessary model to run our inference. So we'll copy these models. Here we get the models. So we will download them. This command consists of setting up the environment for inference on the FPGA, and to load the overlay to the FPGA and all the tools that are required to do inference and compilation of the network. So now we need to run the Caffe model on the FPGA, and this is the quantization and the compilation process. So we will do this from the directory of our, we are already here. Now we'll do there is a script that run the quantization of the FPGA, which is as follows. So here we do the quantization and the optimization of the network before the inference on the FPGA. Now for the inference, once the model is reduced and quantized and optimized, we are ready to do inference. And inference consists of applying one image and try to detect it and identify which class is that picture is. So we will run two examples for a horse and a cat. So here we provide the path to our test image, which is here in that directory. And the successful inference is going to report the highest probability of this class, which is this image that we have. So now this process takes at least 50 seconds. So once it's done, we will run the inference on the FPGA. In the meantime, maybe we can take some questions from the chat. You can ask me any question on the chat window. Do not hesitate. If you have a private question, you can send me an email as well. Okay, so we will take the question after the demo, just to give you more time. So now the compilation and the quantization process succeeded in the previous step. Now we'll run inference on the optimized network. So let's see. So this first one, we'll do inference on the test image that we have offered in the beginning. So the image has a horse and a person. And you can see here the localization of the objects and also the probability. So let's run another example where we have a cat. So if you access the cluster, you can see these images. They are there. So here we have a cat. So this is a demo of this inference. You can try different models with different data sets, and the demo is concluded here. So let's take some questions from the chat window. So we have a question about the access. You can send me a private email if you need access. If you are from a Canadian university, you can access me directly. My email is here. So you can contact me directly to access the cluster. I will provide you with all the instruction and support to get started. But basically, this is fully available today and fully validated. So you just contact me. We can set up a meeting call, and we can go through all the steps to get you started. If you are from industry, there is a click button on the webpage of the cluster that I showed earlier, or you can either contact me via email. And there is a free trial period for people who want to use the cluster. So we have another question from Mehdi. For our project, we need to train a neural network using ImageNet datasets. They have the... Okay, so the question is about the availability of ImageNet datasets on the cluster. As we speak, we don't have the ImageNet dataset on the cluster, but we can easily make it available, and it can be used by anyone. Yes. So please do not hesitate to contact me for any questions around the heterogeneous computing cluster. Either you have a problem that you want to solve, so we can provide support at various levels. We can solve issues related to access, but we can also work with you on your own project to get you started with the right steps and the right frameworks, and we can work together in order to make your adoption of this cluster easy and less painful. I think we can thank all the attendees for attending this webinar today, and we hope to see you soon. Thank you very much.